Now we're good.
Now we're good?
Yeah.
Okay, fine. How to acquire the book? Michelle Thompson, who's my assistant in room 180, has some copies. You may want to get a softcover copy. As you probably know about books, the hardcovers are much more expensive than the softcovers, although the cost to the publisher is almost the same. But they produce hardcovers because they think libraries will buy them, and they make all of their costs, they cover all their costs by selling to libraries. And anytime you buy it, it's almost pure profit. But I would buy a softcover copy. There's no reason, unless you really like hardcovers for some reason. I would get the 5th edition, which we hope is better than the 4th edition, which was better than the 3rd, and so forth. Not only does it have additional chapters in it in addition to those in the earlier editions, but we hope that we've removed not all, but most of the typos in this edition. So with that, that's the book. Now, Sakai. Sakai. Sakai, I don't know, if this is an acronym, I've never understood what it stood for, but it's the website associated not just with this course, but with all courses at Duke. And you should all have access to it. I assume that people in this room do. Is that right? Stockholm, do you have access to Sakai?
Excuse me?
Now have access to Sakai?
Host have access. Yes, we do have the access. Yeah.
Okay, fine. There was one young lady who was talking, apparently did not, but hopefully that's been resolved. Okay, so you need to have access to Sakai because I will send you emails from time to time, and we'll put material on there. Danny will put material on there. By the way, Danny Levin is the teaching assistant to this course.
Hi, guys.
Hi there. And he's going to do all the heavy work. I'm just going to talk about aeroelasticity. And then if I get something wrong in that, he will also tell me about that because you have 10 plus years of experience in industry working on aeroelasticity. So he's a little bit of a ringer. I don't know if you know that word or not. He's not your typical student, right? So he has a little more experience than most. So we'll be doing some interesting things. We'll show you some videos of experiments we've done, for example, but maybe a live experiment too.
Yeah.
Sometime during the
sometimes
semester.
during the semester we'll have a live lecture experiment.
Yeah, and that would be good. So you will be among the select few who've actually seen a live flutter test. So Danny Levin's our teaching assistant. Now I should point out that there's one thing he will not do. He will not grade your homework or your quizzes, and he certainly won't grade his homework. So I will do that. So if you have questions about that, you can ask me. But other than that, you can ask Danny anything you like. By now, you may have discovered my name, but let me write it down. Thank you. And I have an email address, which is the best way to get to me, because I check my email frequently. I don't check my voice messages that frequently. And you're welcome to stop by my office if you're in Durham. That'll be a little more difficult for those of you in Stockholm. And if I'm there, you can catch me. But if you want to save yourself a trip over this way, just send me an email. Let's see, what else should I tell you? Oh, you know about the video lectures, right? We've been doing this course in this format, I think, for about 5 years. And we record the lectures most years, okay? And we recorded them last year. And therefore, I don't plan to actually formally lecture this course this year for a couple of reasons. First of all, I haven't gotten a lot smarter since last year, okay? Secondly, you've got the book, which you can read. And thirdly, I look about this. I'm a year older, but I look about the same as last year. So you'll recognize me in the videos, I hope. Now, 5 years ago, if you got those videos, that might be a little more questionable. So we are going to put the videos on Sakai. There will at least be 2 lectures ahead in terms of putting on Sakai. I think we put the first 6 lectures on Sakai. So you should plan on looking at roughly 2 videos a week, right? 2 lectures worth a week. And then when we come to this class, I'll say, and are there any questions? Now, if there are no questions, then we will reverse roles and I will ask questions, okay? So if you prefer for me to ask questions of you, that's okay, I can do that. Which reminds me, for those of you in Durham, the final exam, not too many, the final exam will be an oral exam. So you get a lot of questions on the final exam. So you might want to practice between now and then. And if you're a Durham, are you all PhD students? No, oh, so we have some answers. Oh, well, I usually tell the students that you should welcome an oral exam because this will prepare you for the qualifying exam and the preliminary exam if you're a PhD student. So for the PhD students, I'll tell you that. For those who are master's students, I'll say, I know you would forever regret not having the opportunity to experience an oral exam. So this is your chance. This is your big chance, right? So either way, we're going to have an oral exam. We'll have weekly homework, which I will assign, and you will work on that. I'll give it to you, probably not assign anything today. We'll see how that goes, either today or on Thursday, and then you'll have a week to work on it. And then I'll give you another assignment, right? Just to keep you busy and out of trouble. Okay, so what else do we need to tell you about? I think that's it. Those of you who are in KTH, as I understand it, you're only going to be with us half the semester, which is fine. However, at no additional charge. If you want to continue to be with us, any of you want to continue to be with us, we can probably arrange that. Yeah. But for reasons which I think I almost understand, it was decided that the students in Stockholm would take the first half of the course this year, which is their first year. And then those who come to Duke in the second year will take the second half of the course. But you're here already because you want to get a double exposure, right? And so for those of you in Stockholm, particularly those of you who may come to Duke next year, and I think there are going to be quite a few. I think there's 6 or 7 or 8 coming next year. You are welcome to attend the entire class if you like, and then I'll leave it to your good judgment as to whether you want to continue to do homework or not for the second half of the course, and we'll work on that when that time comes. I think that's all of the housekeeping logistics that I want to talk about this morning. Are there any questions about any of that? You're all happy? Looking forward eagerly to the oral final exam? Oh, good. I am too. I always enjoy it. Okay. Now, I'm going to give you a chance to ask some questions about aeroelasticity, but let me ask a couple of questions of all of you, both here in Durham and in Stockholm. And there's not a right or wrong answer to these questions. This is an information-seeking question. How many people in Durham know about Lagrange's equations? Oh, everyone's raising their hand. That's good. I won't press you as to how much you know about Lagrange, but at least you know something. How many people know about Hamilton's principle? Oh my goodness, it's a very well-informed group. Okay, here in Durham, North Carolina, these students tell me they all know about Lagrange's equations and also Hamilton's principle. How many people in Stockholm know about Lagrange's equations? I see one reluctant hand going up. Has everyone raised their hand, or are there a few people who have not?
Most of the class, almost everyone.
I would say everyone.
definitely took the advanced vibrations.
Oh, okay. So when you took advanced vibrations with Dr. Keel, you all learned about Lagrange's equation. Okay.
Yeah, the problem is the Lagrange equation was not covered by Dr. Cube. But yes.
You also learned about Hamilton's principle?
Oh, no, not at all. No one knows about Hamilton's principle here.
Not so much. Okay.
No one.
Okay. Well, we'll say a few words about it, but it'll go by fairly quickly unless you slow me down, which is okay. You know, if I'm going too quickly, you say, "Oh, you need to slow down a little bit." That's okay. That's okay. Now, in your reading, you should be reading this book as well as viewing the videos. Lagrange's equations and Hamilton's principle are actually covered in chapter 3. So if you want to use the book to refresh your memory of those topics or to encounter them for the first time, you should look at the first few pages of chapter 3. Chapter 2, in fact, let me write this down. Chapter 2 is based on static aeroelasticity. Now, there is a simpler form of Lagrange's equations and Hamilton's principle which deals with statics. In fact, maybe we'll talk about this in a moment. But the actual discussion of Hamilton's principle and Lagrange's equations are in the first few pages of chapter 3. Yes, sir. Ma'am. Sir.
I'm facing some problem with our projector. We are not able to see the notes. We are trying to adjust the brightness, but I'm not sure it's going to work.
Okay.
Maybe this way.
Yeah, this is a little faint, isn't it? Does that help?
Is it better?
But when you cover the sheet with, well, when you block the light, it looks much... It's too bright. It's too bright.
This is better?
No, less bright.
It's better than it was before, but not perfect yet.
The problem is the brightness is too high, so we have to lower it.
Maybe.
Yeah. Maybe I could. Let's see this.
Can you try turning off the light?
Oh, turn off the lights and that's a thought.
Oh yes. No. Not off the light.
Okay. 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 Yeah. That's better. At least it's better here. I'm not sure it's better in Stockholm. Okay, well, let's go on. Let's talk a little bit about statics. I think maybe that's a little darker. The reason we talk about static aeroelasticity first is not because it's more important. It's because it's easier. No, it's not unimportant. Okay. But it's an easy way to get started in talking about aeroelasticity. So we'll do that first. And in either statics or dynamics, in an aeroelastic system, we're basically interested in two different kinds of situations. One is the system stable or not? Okay. If it's not stable, that means some large and potentially dangerous deformations of the structure may take place because of its interaction with the fluid. And we want to know about that. The other possibility is the system is stable, and we hope that that's true before the airplane finally flies, but it still may be deforming or possibly moving if it's dynamic, and we want to know how much. Because even if it's stable, if motion is too large, stresses are too large, whatever, we still are concerned about that. So in the case of statics, the word that is used to describe the possibility of stability or instability is divergence. So we're going to talk about divergence, and that's covered in chapter 2. And then we're also going to talk about some other phenomena. And the one that's usually of greatest interest to aeroelasticians is the possibility of what is called control surface reversal. And I think I'll not dwell on that for the moment, but we'll come back to that a bit later. The counterpart in dynamics, the question of stability or instability, leads to the concept of flutter. And in fact, I think it's probably true that flutter gets most of the attention from aeroelasticity groups, because if that happens, that's not a good thing. You've had a bad day if your real airplane encounters flutter. And then, in terms of response, assuming the flutter doesn't happen, often you're concerned with gust response. A gust is simply a jargon word meaning the fluctuations that naturally occur in a fluid flow, in the atmosphere or in the wind tunnel, and those fluctuations, which are almost, but not always, random-like, lead to motion of the vehicle, and again, that they can be excessive. Either excessive to the point that the structure is endangered, or more likely the passenger or the pilot is not happy. And we do not want unhappy pilots or passengers. That's not a good thing. Okay, so with that in mind, that's sort of the big picture. With that in mind, let's talk a little bit about Hamilton's principle and Lagrange's equation. So let's start with Hamilton's principle, because in some sense, it's the fountain or the fount of dynamics. And from Hamilton's principle, I can go to Lagrange's equations fairly readily. And then if I want to, I can even simplify further, simplify to statics. And again, the reason we are interested in these quantities is because if you think about it, if we want to determine the motion of the vehicle or the deformation, the first thing we need to know is the equation that governs the motion. We need to know the equations of motion. And either Hamilton's principle or Lagrange's equations are going to be the mechanisms by which we do that. So, Hamilton's principle. It says that there's an integral over some interval of time from time t1 to t2 of a change in kinetic energy plus a change in work, and that must be zero. And it turns out, as you may or may not know, that's equivalent to Newton's second law. It's also the way we can derive Lagrange's equations if we so choose. Now, this del operator I'm sorry? Well, in a moment. You're ahead of me already. Yes. Very good. Very good. The question was, shouldn't there also be some potential energy? And the answer is yes. If there is some potential energy, we should include that. But in principle, the virtual work can take into account potential energy. Usually, it's not the most convenient way to do it, and that's why we explicitly introduce the idea of potential energy. But let's talk about that since you raised the question. I'm going to look at some change in work. We're going to call it, this del operator leads to a virtual change in work, leads to a virtual change. Either a virtual change in work or a virtual change in kinetic energy. But the virtual change in work can be thought of as being two parts. It can be the virtual change associated with conservative forces, which are the ones for which it's convenient to introduce the idea of potential energy. Or the other possibility is non-conservative forces. So C is conservative. NC is everything else. It's non-conservative. Fluid forces, almost always, with not many interesting exceptions, are non-conservative. So that's why we need to think about non-conservative work and non-conservative forces. On the other hand, if you have an elastic structure, which is another part of aeroelasticity, right? It's aerodynamics plus elastic structures. Elastic structures can almost always be described, with one important exception, by introducing the concept of potential energy. Because an elastic structure is like a spring. You know, you deform a spring and you let it go, it comes back to where it started. All the deformation you put into it comes back and is to its original position once you remove the force. The exception to that, of course, is their damping structures, right? And so we have to account for the damping of the structure, and we'll talk about that later on, but basically we make it up. It's the Achilles heel of structural dynamic analysis. We go to all this effort to get kinetic energy and potential energy and go to a great effort to describe those quantities and their implications. And then right at the end, we just sort of throw in a term which, oh, we need some damping. Here it is. Okay. The good news for the fluid side is that in aeroelasticity, often the dominant source of damping in systems is actually from the fluid. As the structure deforms, it moves the fluid forces change as a result of motion of the structure, and part of that fluid force creates an effective damping as far as the structure is concerned. And the usual equations of fluid motion, if we can solve them, which is not easy, will produce a damping which has some rigorous basis. That is, ultimately the damping comes from either the radiation of pressure into the far field or from the viscosity of the fluid or combination thereof. So the good news there is there's a sort of a rigorous theory, if you will, of aerodynamic damping. The more sobering news is sometimes hard to model mathematically. But on the other hand, as you'll see later on, if you don't know the sort, oh, you did take this course in advanced vibrations, right? What did they tell you about damping in advanced vibrations? They pulled it out of the hat, didn't they? Well, not literally, but. Okay, well, we're going to do the same thing. I don't have anything magic to tell you. Well, I have a few things to say later on. Okay, so now the conservative part of the virtual work is usually expressed this way. There's a minus sign. Ask me where the minus sign comes from. Well, it came from the person who did this originally because they thought it was convenient to introduce a minus sign. I don't have to introduce a minus sign. But if I don't introduce a minus sign here, I will fly in the face of hundreds of years of tradition. And when you read the rest of the literature, you'll get confused because I didn't put my minus sign in when everyone else did. So that's where the minus sign comes from. Okay, del U, where U is usually called potential energy. How do we compute del U? Well, what we really do, or someone did, is compute del WC. And then, if you will, this is the definition of del U. I can take the minus. Using higher mathematics, I can take the minus sign on the other side. Del U is minus del WC. So you compute WC. Normally for elastic structures, someone has already done that and written down the expression for U or del WC, and we'll look at those. And so if we do this, then apropos to your question, this is del T now minus del U plus del W in C. So del U is going to come from some structural model. Del T is going to come from knowing the kinetic energy of the structural model usually. And del W and C is going to come from knowing something about aerodynamics. Chapter 4 is entirely devoted to aerodynamics. If you will, it's entirely devoted to computing del W and C. Okay. So that's why we want to know Hamilton's expression. What happens if we have statics? Oh, let me pause here. Questions? Oh. Okay. Any questions from Stockholm yet? Maybe they've fallen asleep. Stockholm, are you okay over there?
Are you?
We don't have any questions. Thank you.
Turn it on. It's not on.
Okay.
No.
All right. Let's move right along then. Here we go. Okay. So now we have Hamilton's principle. Del T minus del U. Well, now we've got the del U in there. Plus del W's in C. Oh, sorry about that. Thank you. dt equals 0. But now let's specialize to statics. What do we mean by statics? By statics, we pretend like nothing changes with time. Okay? Well, when we do dynamics, we'll see that there's some qualifications to that statement, but for the moment, let's just assume that nothing's changing with time. Okay? It's just whatever's happening is not changing with time. If nothing is changing with time, then what happens? What are the consequences of that? Nothing changing with time. That means there's no kinetic energy, right? I mean, nothing's moving. Kinetic means something about motion, right? No kinetic, oh, sorry about that. Energy. So T is 0, del T is 0, and this interval over, well, and therefore there is a del U and there's a del W and C, but they're not changing with time, right? So we can take those outside the integral, and then the integral is just dt T1, T2 minus T1, but that's just some number, right? We're all going to set to 0 anyway. So that implies that minus del U plus del W in C is 0. So that's statics as Hamilton would have it. Well, this is pretty abstract. So why don't we do an example? You did ask me to do an example, didn't you? Yes, thank you. Okay. Let's do an example that's relevant to aeroelasticity, and there are going to be several of these. So let's look at some simplified model of an airfoil or a wing, right? Or possibly a wing. One could construct a thin, flat plate and that's a pretty simple but possible model of an airfoil or wing structure, and it's placed at some angle relative to an oncoming flow. And now I will make an aside to warn you of something that's likely to happen in this course in this field from time to time. We're going to use the same symbol to mean two different things. But you're being ever alert. You will never confuse the symbol. It mean one thing or it should mean something else. So U is traditionally used as the potential energy symbol. Okay. It's also used as the mean flow velocity of a stream. Remember what happened. Aeroelasticity didn't exist forever, right? Before aeroelasticity, there was just the structure people over here and the fluids people over here, and they all developed their notation independently. And then when they got together and created the field of aeroelasticity, they discovered they using the same symbol to mean two different things. But you're not going to be confused by that. Okay, so and then we need some elasticity for this elastic structure. And the simplest model of an elastic structure is to represent something that that has a spring-like characteristic. So we're going to literally have a spring. So we'll have a we could do a couple things. We could put a spring like this. We could put a spring like that, right? That would give us some elastic characteristics. But for reasons that will become more clear later, we're going to put, rather than two translational springs, we're going to put one torsional spring. So this is a torsional spring. What do we mean by a torsional spring? We mean that when this plate rotates, there's a spring that's resisting that torsional deformation. Okay? And K sub alpha is the torsional spring constant. Okay? And now the question is, what is the potential energy associated with the torsional spring? And the answer, if you've read the book, no. Or maybe you know from having that course in vibrations or some other course. And so what is the potential energy associated with the spring? If it's a nice linear spring, in case of alpha, it is.
Can I answer?
Yeah, absolutely.
1/2 of K alpha squared.
Very good. Thank you. Now, does everyone agree with that? Why not? Now, you could have some additional terms. You could have a cubic term. You could have a quartic term. You know, if you want to have a nonlinear spring, right? You can think of this as the first term in a Taylor series. Okay. But where did this come from? Aside from the fact that someone told you that's the right answer. Well, yes, could be confused from the virtual work or the work done by this spring. We could. So let's just do that for fun and fun. Yeah. Thank you. So where does it come from? Well, we could compute the work done by that torsional spring. So what happens when the spring when the spring rotates, or when the plate rotates, and therefore the spring also rotates, right? Then there's a moment which, according to a linear spring, this is M sub alpha. This is the moment created by rotation of spring Okay. And that's equal to K alpha alpha, except we do have to think about the minus sign, or plus or minus sign. This moment is resisting, it's the nature of an elastic spring, it's resisting the deformation. So if I rotate the flat plate, the torsional spring deforms in a certain direction, then the moment is in the opposite direction, right? So we're going to put a minus sign here. Now we could adapt a different sign convention, but we don't want to do that. And the reason we talked about del W equal minus del U, because we wanted U to be a positive quantity. That's really, it was a cultural decision. Okay, so that's that. Now, what about the work done by the spring? Well, the work is M sub alpha times a little bit increment of alpha, d alpha is a differential. And then we have to integrate from 0 to some final value. And so this is the integral then of minus K alpha, alpha, d alpha, from 0 to some final value. And using higher mathematics, that's minus 1/2 K alpha, alpha final, really, right? Squared. Although usually we get a little lazy and delete the subscript, right? Okay. But this is now the work done. And we choose to define potential energy as the opposite of the work, because we prefer to have our potential energy be a positive number. But that's tradition. That's a cultural decision. It has nothing to do with anything more basic than that. So this is the work done, and by definition, this is minus the potential energy, and hence we're all right. Now, there are a couple of things we might say about this. One thing we might say about it is, well, that's fine, but what about del W? I mean, this is real work, right? This is the actual work done. Del W, if you've not had Hamilton's principle before, this may be a little disconcerting and uncomfortable, but get over it. By then, of course, you'll be true believers. I hope. You know, some of you already are almost true believers. Del W is imagined. It's only in our mind. It never happens in real life, right? But it's still very useful. So del W is the work done when system undergoes an imagined deformation. Mm-hmm. Now, usually we don't use imagined because probably people thought if you start talking about imaginary work, that would get people even more upset. So using the word, rather than using the word imagine, we usually use the word virtual. At least that's the word in English. I don't know what the word is in Swedish or other languages. What is it in Portuguese? I have no idea. Much of the engineering scientific literature is either in English or it's been converted from English into some other language. If you read Russian, I read Russian just enough to be dangerous. Almost all the technical words are English words written in the Cyrillic alphabet, but if you pronounce it, it's mechanical. It's whatever. So I suspect it's virtual in Russian too, if you knew how to pronounce it correctly. Anyway, okay. So, in this case, if we want to compute virtual work, we say the virtual work is equal to m alpha times del alpha. Okay, but notice we have a hybrid. We have a hybrid quantity here. This m sub alpha is the real moment. It's the actual physical moment. Okay. Actual or physical moment. But del alpha is an imagined or virtual deformation. Okay? Okay. Let's keep that in mind. By the way, Danny has volunteered to copy my notes and put them on Sakai.
Yeah.
So if you're welcome to make all the notes you want to, but there's a book. You can have my notes on Sakai. And so copying every little scribble I make down, unless you find it helpful for some reason, you don't want to leave it. So I should have said that earlier on. Sorry about that. Okay, so let's go one more step. Del W equals m sub y del alpha. Okay? All right. Now, let's look at U. Oops, I'm sorry. Thank you. You recall, U we decided was going to be 1/2 k alpha alpha squared, right? Now I'm going to compute del U. Why? Because I said I needed that a moment ago, right, when I was looking at Hamilton's principle. So using higher mathematics, we're going to compute del U. How do I do that? I treat del from the standpoint of an operator just like it were a differential, right? So if I take del of this right-hand side, I get 1/2 k alpha times 2 alpha times del alpha, right? So the del of alpha squared is 2 alpha times del alpha, right? And then using higher mathematics, I can cancel the 2's. And note what I have here. What do I have? I have del U equals k alpha alpha times del alpha. What is that? It's minus the moment, right? Minus the moment, because that we chose to put the minus sign in the relationship between moment and alpha, right? So this is minus m sub y del alpha, which is also minus del W. Conservative, actually. Okay, so it's all coming out the way we hope, at least the way I hope. I hope it's the way you like as well. While we're here and anticipating what we'll do later on, although this is not really static, why don't we try to compute the virtual work done by a damping force? This is what we've done now is we've computed the virtual work due to this elastic spring, right? But whatever mysterious physical source is giving rise to damping in the structure. And it could be because the structure, when it moves, rubs against something, there's some friction. Who knows? It could be some internal damping in the material itself, which is usually not very important in Aeroelasticity. although there are people who spend their careers thinking about that. But it's largely a waste of time for most practical engineering stuff. Not necessarily for nanoscale devices, I mean, but for a real airplane. So what we have to think about, if we want to compute the virtual work due to damping, well, we can, it's minus m sub alpha. I'll put a D up here to remind you we're talking about damping now. Damping. This is not the m sub alpha we were talking about a moment ago. This is now the m sub alpha associated with damping, right? Times del alpha. Or if you want real work, it's integral m sub alpha damping d alpha, right? From 0 to some final value. Okay, help me out here. What expression would you like to use for this damping moment? Well, the idea is there's no damping unless there's real motion, right? Most damping forces or moments are thought to be proportional to the time rate of change of the deformation, right? So we kind of think it may be m sub alpha d is proportional to alpha dot, right? That's the simplest dependence on alpha dot I can think of, right? It's linear. Okay, that's good. And we can, if you don't like proportional, and we can introduce some coefficient. Right? Where does that come from? Well, we asked somebody who's more experienced than we are, what do you think a good value for that would be based on the last airplane we built or whatever? Okay. But for our purposes, let's just leave it like that. So now we can compute the virtual work or we can compute the real work. Let's compute the real work first. The real work is this thing, which is this thing. Well, let me write it down again. It's the integral of from 0 to alpha final of m sub alpha damping d alpha, which is equal to the integral from 0 to alpha final of c alpha dot times alpha dot d alpha. All right? Okay, now your first homework assignment is to evaluate that energy. If you do that successfully in analytical form, you will become famous because no one else has ever been able to do it. We give you easy homework. You can try it. And don't give up until you spend at least an hour on it. But, or spend as much time as you like. I mean, here's your chance. Here's your first chance from this course to become famous. But don't be too discouraged if you don't. On the other hand, you can say something about this. Let me rewrite that equation and continue the conversation. Okay, so this is the work due to damping based on our damping model, right? And it's equal to from 0 to alpha final of C alpha dot times alpha dot D alpha, right? Well, we could play this game. We're allowed to multiply and divide by the same quantity, right? So if I wanted to, I could rewrite this by dividing by dt and multiplying by dt, and then I could write this as 0 alpha f c alpha dot times alpha dot squared, right? That's alpha dot dt. So what do I know? Well, if this is a positive coefficient, which it is for most models. What? That's not true. Yeah, well, what is that coefficient? Is it positive or negative? Sign of that coefficient. What is the sign? Well, we want the moment to resist the motion, right? We want the damping moment to also oppose the motion. We want the damping motion to be in the opposite direction of C alpha dot. Opposite in direction of alpha dot. So if we say M damping is C alpha dot, if this is to be in the opposite direction of that, then this must be less than 0. So what does this say? This says the damping does negative work. Energy is dissipated, right? Energy is dissipated. So we can conclude that, but there's no potential energy associated with the damping term. It's non-conservative. So the only thing we can really do is represent damping by saying del W NC due to damping is what it is. In this case, it would be C alpha dot times alpha dot times del alpha. Right? And so when we develop our equation of motion later on using Hamilton's principle or whatever, we'll have an expression for the virtual work associated with this non-conservative damping force, but we won't have a potential energy. Okay. All right. Now, let's return to statics. Hold on a moment. Go back to our plate and our spring. And we've concluded that del U, well, is K alpha del alpha. We also know that because it came from 1/2 K alpha squared. And if we're going to do aeroelasticity, we need to say something about, we need to say something about fluid. So this takes care of the, if you will, our structural model. It's a pretty simple one, but it takes care of our structural model. What about the fluid? Well, we have to compute the virtual work due to the fluid, but that's going to be the aerodynamic moment, or the fluid moment, times del alpha, right? And just to confuse you, after all, remember aerodynamicists and structural people grew up separately and didn't talk to each other until later in life. It's usually the case that the aerodynamic moment is taken as positive in the same direction as the motion, or in this case, the static. It's the angle of attack, right? So this is M aero is positive by convention or tradition. In the same direction as alpha. Okay. And if you've been reading chapter 2 faithfully, I know you have, or well, how many people have taken a course in aerodynamics at some point? Okay, good. How many people in Stockholm have taken a course in aerodynamics, at least study flow aerodynamics? Not everyone, huh? Okay, well, you're going to learn some aerodynamics in this course. That's a good thing. I'm going to tell you what this moment looks like. My friend, the aerodynamicist, told me. It looks like this. First of all, it's the lift, which is the vertical force acting on my airfoil, times the distance, E, which is the distance from where the lift acts. It's the, if you will, it's the center of pressure. So it's the distance from here to here. And the lift itself, my aerodynamicist friends tell me, is proportional to alpha. In fact, the reason airplanes fly is because there is some lift as a result of an alpha. If that didn't happen, we'd still be on the ground, right? And there's a coefficient which comes from aerodynamic theory, and that theory could be something as basic as dimensional analysis, or it could come from solving some equations of fluid motion, but it looks like the following. It's 1/2. There are 1/2s in aerodynamic theory, just as there are in structural analysis, times the density of the fluid, times u squared. I'll put a sub-infinity on these so we'll know we're talking about fluid. This is flow velocity. Times c, which is the chord of this airfoil, times some constant. And the constant, you could argue, it has to be of order 1, although I'm going to press the definition of order 1 a little bit here. It turns out in low speed flow, low speed meaning I'm well below the speed of sound, it turns out to be a number like 2 pi. Okay. And then, of course, most importantly, it's proportional to alpha. So, rho infinity, u infinity squared has dimensions of pressure. And so, by tradition, this is called misleadingly dynamic pressure. So, 1/2 rho infinity, u infinity squared is often given the symbol Q, just so you don't have to keep writing all the symbols independently. And it's called dynamic pressure. Later on, when we talk about fluid dynamics more generally, we'll give some rationale for that name, although it's basically fairly misleading. And when the Wright brothers, remember the Wright brothers? When the Wright brothers were doing their work, they had a wind tunnel. They were one of the first people to actually use a wind tunnel. I think the first wind tunnel was by Eiffel, as in Eiffel Tower. We looked at the wind loads on the Eiffel Tower, which he was concerned about, as he should have been, right? Anyway, if you do some wind tunnel tests, if you put a flat plate in the wind tunnel at an angle of attack, you find that if you vary the angle of attack, vary alpha over some range up to about typically 10 or 15 degrees, that indeed, and you measure the lift. The lift is proportional to alpha up to that angle. Once you get beyond that angle, all sorts of other ugly things happen that we won't talk about just yet. You also find that if you vary the chord of the airfoil in the wind tunnel and measure lift, that indeed the lift is proportional to the chord. And you find it's proportional to the square of the velocity. Now, in the wind tunnels that the Wright brothers had, they couldn't vary the density. But you can argue on physical terms that the denser the flow, the larger the forces, right? I mean, it's not, you don't have to be too insightful to think this might be proportional to infinity. Okay, so if you do all this, if you know the density of the fluid and you measure it U infinity, you measure it C and alpha and all that, and then you measure the actual value of the lift, you can determine what this constant is. And it turns out to be, it's not quite 2 pi, that's sort of an idealized number. It's a little less than 2 pi typically, but you know, it's 5.7. It's not 6.28, but hey, close enough. Right? On the other hand, if you're the Wright brothers, you really want to know it's 5.7 rather than 6.28. But the theory that we'll go through later, it says it's 2 pi. Okay, so with all of this, we can go back and determine an equation of static equilibrium for our simple model. So what is it again? It's delta W in C minus del U plus that equals 0. We determined that del U was what? It was K alpha alpha del alpha, and del W in C is L times E, which is 1/2 rho infinity U infinity squared C 2 pi alpha. Times del alpha, right? That's important. And if you take these two quantities and put them in here, you have what? You have K alpha alpha with a minus sign plus 1/2. Oh, I'm going to use my symbol Q so I can, right? Remember what Q was? Remember what Q was. C 2 pi, there's an E, alpha, all of that gets multiplied by del alpha equals 0. All right? And if this is imagined, right? It's not only imagined, we are allowed to freely imagine. This can be considered arbitrary. And if this is arbitrary, it can be anything we like. The only way this can possibly be 0 is if the coefficient is 0, right? So that gives us our equation of equilibrium. But then we can apply a similar but philosophically distinct argument. We can now rewrite this as minus K alpha plus Q infinity C 2 pi E, and both of these things have an alpha in them, right? Alpha equals 0. And now we can make the following argument. One possible way for this equation to be 0 would be if alpha was 0, which is not terribly interesting, but it's true, right? The other possibility is this coefficient might be 0. If this coefficient is 0, then alpha can be anything and this equation can be satisfied. If this can be anything, it might be way bigger than we want it to be. Okay? That would not be good. So having this coefficient set to 0 gives us some sort of a critical condition. In fact, it tells us for a given spring constant and a c and this to t and 2 pi, it tells us there's a value of dynamic pressure where alpha might be bigger than we want it to be. That's divergence. And there's a counterpart to this kind of discussion in dynamics, and that will lead to flight. But this is, for those of you who study eigenvalues and eigenvectors, this is an eigenvalue problem, right? That is, there's a special, for example, there's a special value of Q where non-trivial, non-zero solutions of alpha are possible. Okay. So within the framework of linear models and aeroelasticity, we're almost always led to a eigenvalue problem. And this is probably the simplest one that we can conjure up. Now, you got me talking all this time. I was supposed to be responding to questions. So now, at the end, are there any questions? And none in Durham, North Carolina. Are there any questions in Stockholm before we conclude for the day? Hearing none?
I have a question, Prof.
Yes.
Since divergence is a static instability and this equation is modeling divergence,
yes,
and it's an eigenvalue problem, we have frequencies, but our frequency is going to help for a static problem of divergence.
Yes. What was the question?
What's the frequency of the
Oh, what is frequency? Ah, very good. The answer is the frequency will turn out to be 0. But let me tell you what's really happening. And in fact, this will be a good homework problem. We'll let you do a dynamic analysis of divergence, which is apparently a static phenomenon, right? Okay, but let me tell you what's happening, and then we'll go on from there. If it is interesting to think of, it is interesting to examine these static phenomena from a dynamics point of view, because it does give you some additional insight. The reason we tend to do the analysis starting with statics from the outset is because it simplifies the mathematics. But it probably causes some loss of physical insight, right? So here's what's really happening. If we were to plot alpha over here, and it really does depend on time to some degree. Ah, thank you. Okay, fine. And here's time. If I gave this flat plate some initial alpha, just nudge it a little bit. If I were at a value of dynamic pressure less than the divergence condition, right? We know how to compute Q divergence, right? We just saw mathematically how to do it. If I were at a value less than that, and I started out with some initial alpha, here's what would happen. There would be some damping in the system, and there would be motion, and it would decay. And associated with this, there is a period, right? There's a period of this oscillation. And from knowing the period, let me call it T for period. The frequency would be 2 pi over the period, okay? We cannot get information, though, from static analysis. We need a dynamic analysis to do this, right? Okay. but be patient. Now I go to Q infinity. That's still less than Q infinity divergence, but it's higher. It's higher than this one, right? And now I do the same plot. And a couple of things happen, typically. One is I probably don't draw it. The point is that the period, right, this period gets longer. But if the period is getting longer, the frequency is getting shorter or smaller, right? And then if I'm right at divergence, and I start here, it doesn't decay at all. And if I'm above divergence, I'm going to make that a solid line. I'll make this a dashed line. If I'm above divergence, it actually grows exponentially with time. There's no frequency. The frequency is zero once I'm in the divergence. And it's because of this behavior that I can get away with a static analysis. But by doing the static analysis, I lose my ability to know all of this, which means I'm losing some physical insight, which may be important. But so you will not ever lose that physical insight. I'm going to allow you as your first homework problem to do a dynamic analysis of divergence. And that will allow you to compute these plots. How about that? Aren't you glad you asked that question? You're supposed to say yes.
Yes, I'm happy.
Oh, good. Thank you. Thank you. Are there other questions?
Yeah, one more question.
Okay.
Since divergence can be analogous to a buckling effect, which a buckling force has, but for divergence to happen, it was said that you have a force which is acting at the center of pressure. What is causing the beam to buckle and not bend? What I'm trying to ask is, at the unsupported end, what is the force which is keeping it from not deflecting? So you have a buckled profile.
Oh, you're saying if I have a real airplane, when it has a tendency to diverge, it really won't go off to infinity, but it'll buckle at some finite deformation. Is that your question?
My question was when a wing is undergoing divergence, it has a buckled profile, but buckling is due to a compressive load.
Yes.
But divergence is caused by a lift force, which is acting somewhere in the mid-span of the wing.
Yes.
And what is causing it to have a U profile rather than a inclined profile?
Well, I'm not sure I understand your question, but let me try to answer it in two ways. Let me rephrase your question in two different ways and answer both of them and see if one of them is the way you were thinking of. As you point out, the divergence is caused by the aerodynamic forces, right? Interacting with the elastic forces. Buckling, if you think of buckling of a beam, of course, this is because you apply a compressive load. And it is true that from a mathematical point of view, that compressive load and the aerodynamic forces are providing a similar phenomenon, namely a static instability. In one case, when it's a compressive load, we call it buckling. And in the case of aerodynamic forces, sometimes people actually use the phrase buckling, but it's more traditional in aeroelasticity to use the word divergence. But much of the mathematical modeling of buckling and divergence are virtually the same. Now, as to why the aerodynamic forces can do that is that it's really a matter of where the lift force is placed. Let me go back to my picture here. Here, if you remember this picture, I cleverly put the lift force ahead of this point for the spring to be connected. If this lift force were behind this spring, the lift force, when this flex upward, the lift force would actually create a moment of pushing back down. And you never get divergence if the center of lift is behind the spring point, which in the aeroelastic literature is called the elastic axis. And that deals with the sign of this distance, E, right? If E, I define E as positive when lift is ahead of the spring connection point, but if E were behind, so that E was negative, if this point were behind the elastic axis and E were negative, then I would never get divergence. Okay? Now, that's one answer. The other question I thought you were asking was, all of this is based on a linear model, as the spring moment is proportional to alpha, the aerodynamic moment is proportional to alpha, so everything is proportional to alpha. And within the framework of linear theory, all we can do is predict what happens up to the point where this thing begins to diverge. If you have a nonlinearity in the structure, which you might have, then this would not go on forever. It would at some point reach a finite value and stop, because the nonlinear spring characteristics would be more than sufficient to offset the negative tendency of the aerodynamic force. So we've left out nonlinearity. So in both flutter and divergence, sometimes you don't go off to infinity as linear theory predicts, but you go to some finite value. Even so, most aerospace companies do not like to fly their airplanes at values of flow velocity beyond the divergent condition or beyond the corresponding flutter condition. Now, did I answer your question at some point during that that discussion?
Yeah, I think so.
Okay, good.
Yeah.
Okay.
Thank you.
Well, feel free to try again. But maybe not today.
Maybe I'm not able to phrase the question properly. I think maybe I can write a mail later on.
Okay, that'll be great.
Excuse me. Excuse me.
Okay.
Hello.
Okay, any other questions?
Can you hear me? I have another question.
Okay, fire away.
Yes. I think in this case we are treating a 2D flat plate problem, but is there any 3D effect in reality? I think the lift coefficient will be different. And I mean, it's not 2 pi in reality. And is there any additional effect?
Oh, absolutely, absolutely. Yeah. Later on, let me draw a picture. Oops. Yeah, absolutely. I mean, we've used this model for simplicity. We use this model where we're thinking of this as maybe as a wind tunnel, and as the airfoil spans the wind tunnel. But a more realistic model, looking down on the top view, would be, here's the side wall of our wind tunnel. And here's a plate. It's a flat plate. It's clamped at this edge. It's free at this edge. Here's the other wall, the wind tunnel. And yes, the aerodynamics at this tip will be important quantitatively, and you're right. With a finite aspect ratio, the 2 pi factor will be 2 pi. Will be less than 2 pi. It'll be something less than that. And again, if you have an appropriate aerodynamic model, you can model that as well. Yeah, absolutely.
Okay, thank you.
You're welcome. Any other questions? Okay, well, you've got more than
Can you hear me?
Yep. Hello?
Hello, I have another question. When you arrive to the final,
Yes?
but I can only see scalars there. Can you explain how that turned to be an eigenvalue problem?
Final question turns out to be eigenvalue problem.
Oh, how? Well, yes, I'll try. Let me go back to wherever I was. Okay. Yeah. You're looking at this equation? Are you looking at this one?
Yes, that equation.
Yeah. But it's an eigenvalue. What I mean by an eigenvalue problem, an eigenvalue problem is where you have some measure of deformation or response of the system. In this case, it's alpha. And then there's a coefficient that multiplies it. And an eigenvalue problem is when, if you will, the right-hand side of the equation is 0, and there are two possibilities. Either alpha is 0 or the coefficient is 0. And the eigenvalue problem is when you consider the case alpha, or the deformation more generally, not being 0, and therefore the coefficient must be, and therefore you look for a critical value of some parameter in this equation which allows this coefficient to be 0. And from a physical perspective, the interesting parameter is the dynamic pressure. It's the flow condition where alpha can have values other than 0. Does that help?
Yes, thank you.
Do I dare ask this? Are there any other questions?
One final question. Divergence, if it happens in a wing, does it happen along the chord or does it happen along the span?
Does it happen along the chord or along the span? The answer is it happens everywhere. When you have divergence, then the entire structure is in a divergent state. It's not that one point in the structure is and something else is not. It's the entire system is divergent.
Okay, thank you.
You're welcome. All right. Any more questions? Hearing none. We will declare the meeting closed, but we'll look forward to seeing you again on Thursday.